What is electrostatics? Electrostatics is the study of individual charged particles. The two most common charged particles are the proton and the electron. Now they have the same charge, 1.6 times 10 to the negative 19th coulombs, but the proton is positive and the electron is negative. Charge is conserved, so it can't be created or destroyed, and charge is also quantized. What that means is that charge only comes in increments of 1.6 times 10 to the negative 19. So I can have a particle that has 3 extra electrons, or 10 extra electrons, or even 1,000 extra electrons, but I can't ever get a half of an electron. I can't split that charge into a half or a quarter. It only comes in whole electrons. That's the only way we can transfer charge, is in these chunks. Net charge means we have, net means unbalanced. So if an object has a net charge, it either has more positives or more negatives. The only thing that we transfer is electrons. So if you have a negative net charge, that means you gained electrons, and if you have a positive net charge, it means you lost electrons. These are the 3 forms of charging an object: friction, conduction, and induction. Now, surrounding an electric charge, we have something called an electric field. And there's some rules that you need to know for electric fields. They start on positives and they end on negatives. The lines will never cross, so you'll see them bend and they'll deflect each other, but they'll never cross over each other. The density of the electric field lines represents the strength. So if you have lines that are very close together, that represents a strong field. And if you have lines that are more spaced apart, that represents a weaker field. The electric field always points tangent to the lines. So if you're looking at what's the electric field right here in the diagram, the electric field points tangent. Or if you want to know what is it right here, you just draw a tangent line to the pattern that you see. Now when you hear electric field, you should think force. It forces a charge. Electric fields provide a force. We have a very simple equation. The force is equal to the charge times the electric field. Now, don't ever plug in the positive or the negative sign into the equation. Just remember that positives get forced in the same direction of the field, and negatives get forced opposite the field. Okay, give these 2 problems a try. Go ahead and pause your video and try and solve these 2 problems. So you should have attempted both of these problems. Problem number 1, an electron is accelerated from rest for a time of 10 nanoseconds by an electric field that exerts a force of 8 times 10 to the negative 15 newtons. Okay, so we know the time, and we also know the force, and we know it's an electron, so we also know the charge. Okay, what is the magnitude of the electric field? So force equals charge times electric field. So electric field equals force over charge. And I know both of these things. So the force is 8 times 10 to the negative 15 newtons. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. Go ahead and divide these. It looks like we're going to get 5 times 10 to the 4th 5 times 10 to the 4th newtons per coulomb. Choice E. And now we're looking for the speed of the electron after accelerating for the nanosecond. Okay, I'm going to use kinematics to solve this problem. So write down your variables: displacement, initial velocity, final velocity, acceleration, and time. And let's look at what we know. We know the time is 1 times 10 to the negative 9 seconds. And we know that it starts from rest. So I know the initial speed is 0. And I'm looking for the final speed. That's what I'm trying to find. I have to know 3 things to find a 4th. So the third thing I'm going to find is I'm going to find the acceleration using the fact that I know the acceleration is force over mass. In this case, it's the mass of an electron. So they give me the force. The force is 8 times 10 to the negative 15 newtons. And the mass of an electron, you can look it up on your table of information, but it's 9.11 times 10 to the negative 31 kilograms. And let's see what acceleration that gives us. That gives us an acceleration of 8.78 times 10 to the 15th power. So I want to put that into my chart. 8.78 times 10 to the 15th power. Meter per second squared. I know 3 things. I can always find a 4th. Just figure out what star equation you want to use. I'm going to use the first star equation. V equals V naught plus AT. V naught is 0. So the final velocity is just going to be the acceleration. 8.78 times 10 to the 15th times the time. 1 times 10 to the negative 9th. I'm noticing that this is an estimation problem. All we have here are order of magnitudes. So I probably didn't need to use my calculator up here, but I'm gonna go ahead and finish it up. And this is gonna give us about 8.8 times 10 to the 6th power meter per second. That's approximately, let me round this, that's approximately 10 times 10 to the 6th power. And that is equal to 1 times 10 to the 7th power. Same thing. And so looking at the answers over here, here's 10 to the 7th power. I'm going to go with D. Alright, here we are, second page. So conductors are metals, and metals have free electrons. Electrons that can move from atom to atom. Now, when you have a conductor that has a net charge, a special thing happens. So let's say I have a conductor that has a net negative charge. All the negatives are going to distribute themselves evenly on the edges. If I had a conductor with a net positive charge, all the excess positive charge will distribute itself around the edges. The extra charge will never be anywhere else, just on the edges. And another property that you should know is that within the conductor, the electric field is always 0. So remember that. You get a conductor, charge goes to the edge evenly, and inside the electric field is 0. Okay. Now, when you think, so let's go back for a second. When you think electric field, I want you to think that forces a charge. Electric fields give us a force. When you think voltage, I want you to think energy. Voltages give charges energy. Okay. And here's the equation. charge times voltage, or change in voltage. Positive charges fall, if you want to think of it like that, from high voltage to low voltage, or from positive voltage to negative voltage. And negative charges fall from low to high voltage, or negative to positive. So just think, positive charges do what you would expect, go from high to low, and negative charges do the opposite, low to high. And we can solve these like energy problems just using conservation of energy. So we've talked about electric field. This gives a charge a force. We've talked about voltage. This gives a charge energy. If we want to relate electric field and voltage, we use this equation. Electric field is voltage difference, potential difference over the distance. Now we only use this if the electric field is uniform, meaning parallel plates like we have in this problem here. So give this problem a try and pause your video now. Hopefully you were able to solve this problem. We have parallel plates with an electric field pointing to the left. Now we know the relationship between electric field and voltage, so I'm going to just right away find the voltage. So the delta V equals the electric field times the distance. And the electric field is 5,000 newtons per coulomb, and the distance is 2 centimeters, or 2 times 10 to the negative 2. And that is going to give us, let's see, 10 times 10 to the first power, or 100 volts. So there's a 100-volt difference between this plate and this plate. This over here is going to be, electric fields always point away from positives, so this is going to be my positive plate, or my higher voltage. This is going to be my negative plate. So I'm going to call this plate over here plus 50 volts. I'm going to call this plate over here negative 50 volts. Okay. Or it doesn't matter what you call the plates. You could call this one over here 100 volts and this one 0 volts, as long as the difference is 100. Okay. Now an electron is released midway between the plates. So here's our little electron E. Put a little negative sign. Determine its speed just before striking one of the plates. So electrons fall from, they're negative, so they fall from low to high. So the electron's going to go this way to the right. We want to know its speed when it gets over here. So I'm going to use energy. Potential energy initial equals kinetic energy final. Potential energy is charge times voltage. Kinetic energy is 1/2 mv squared. The charge of an electron, so first I'll solve for V. So solving real quick, V equals the square root of 2q delta V all over m. Plug in our numbers. 2 times the charge of an electron, 1.6 times 10 to the negative 19th. The voltage difference, now don't use the full 100 because the electron only started halfway. We've got to use 50 volts. And then divide by the mass of an electron. Again, you can look this up or just know that it's 9.11 times 10 to the negative 31st power. So I'm just going to plug these into my calculator now. And I'm getting 4.2 times 10 to the 6th power meter per second. Okay, if you have 2-point charges, the way that you find the force is by using Coulomb's law. Keep in mind that K can also be written as 1 over 4 pi epsilon naught. Either way you write it, it still means 9 times 10 to the 9th. Please do not put the positive and the negative charges into the equation. Just use those to figure out if they attract or repel. Okay, then ignore the negative and positive after that. Remember that the force on each charge has to be equal and opposite because of Newton's third law. So it doesn't matter if I have a big old plus 10Q over here, and over here I have a 1Q, here a big charge, here a little charge. They're still going to feel the same repulsive force because of Newton's third law. Go ahead and try this problem. Before you do, this should say find an expression for the force on particle 1 due to particle 2 and state its direction. Go ahead and try this problem. Pause your video now. You should have attempted this Coulomb's law problem. We've got two charges. We want to know what's the force on particle 1 due to particle 2. Okay, so two charges, Coulomb's law. F equals K Q1 Q2 over the distance squared. Now this is a variable problem, so use the variables that they give you. So the force equals K. Q1 is just Q, big Q. Q2 is also big Q, all over the distance squared. Now I don't know the distance yet, so using a little bit of trig, I make a right triangle, and I can see that the bottom of that triangle is L sine of theta. I have the same triangle here, so I have another L sine of theta. So the distance is L sine theta plus L sine theta. Got to square that distance. Simplify, I get K Q squared in the numerator. In the denominator, I've got 2L sine theta squared. And if I'm going to simplify that one more step, K Q squared over 4 L squared sine squared theta. Everything gets squared except for the K. And that's my answer. Now, it also said state its direction, and since they're both positive, they are going to repel. So particle 1 is being forced to the left, or the negative x direction. More point charge equations. So first we had Coulomb's law. Now we have the electric field of a point charge. So that's kq over d squared. And that looks very similar to the voltage of a point charge, only the distance isn't squared in this one. But there's a major difference between the electric field and the voltage of a point charge. Electric fields are vectors, and voltages are scalars. Okay, so you have to think about the direction when you deal with electric field. You do not have to worry about direction at all with voltage. Go ahead and try both of these problems. Read through these points, try the problems. Go ahead and pause your video now. I hope you're able to solve both of these problems. Problem 1 deals with electric fields. We have a charge plus Q, a little point charge, and it wants to know if we look at a point twice as far away, what happens to the electric field strength. Okay, so at point A, the electric field, since it's a positive charge, points away. I'll call this electric field at point A, E of A. So electric field at point A is K times Q all over the distance squared. And of course that's going to the right. Okay? Now at point B, I'll call that E of B. Now, since the distance is bigger, the electric field is going to be smaller. So I still have K, I still have Q, and now the distance it's doubled, 2D squared, and that's going to be KQ over 4D squared, still to the right. And so if you compare these two equations, this is KQ over D squared, this is KQ over 4D squared, A to B, this is 4 times greater than B. So the answer is 4 to 1. Here we have a voltage problem. They're calling it electric potential. But remember, voltage goes by a lot of names. Voltage, electric potential, even EMF. Those all mean voltage. We want to find the voltage at point A. The way that we do that is by adding the voltage of each charge. So the voltage at point A equals the voltage of charge 1 plus the voltage of charge 2. Now the voltage of charge 1 is going to be K times Q1 over its distance, and the voltage of charge 2 is going to be K times charge 2 over its distance. Notice that the distance is squared in electric field, but it's not squared in voltage. Now I'm going to use the variables that they give me. So K times positive Q over the distance, and again, same right triangle as before, so the distance is L sine theta, and the voltage of this is K times Q over same distance here, L sine theta. They're both positive, so they both give me a positive voltage. So I get, with my common denominator, 2KQ over L sine theta. If one of these were negative, or if both of them were negative, I would put the negative sign into the equation. Voltage is the one equation in the whole unit that I want you to put either the positive or negative into the equation.